Hello, everybody. Thanks for coming. I'm Kem Raj. I work for Comcast, primarily on RDK platforms. So RDK is actually a very generic media platform that's how it started. Basically, the Comcast set-top distribution. And today, actually, we are going to talk about the RDKB, which is the broadband profile of RDK. And so it's an introduction, what all features it has, and how we are doing things to connect to our backends and all the gateway management and stuff like that. So what we are going to cover is what is RDKB and what are its unique features, why we should use RDKB, what are its advantages, and then we'll also have like high-level component architectures as well as go over the specific zoom into the middleware, what we call RDKB. And then we'll go over some information about how to get access to it. And so meanwhile, throughout the talk, you can ask questions at any time. I have another mic here. I'll just circle it around. So RDK program actually at Comcast started with the video platform. So we have since then evolved it into another profiles of RDK. And one of these profiles is the broadband profile, and then we also have camera profiles and others, which are more interesting to specific segments of home security and stuff like that. Ties into RDKB in general, but I'm not going to cover that much on that side, but essentially talk about the gateway part of it. So it shares the most common infrastructure, the build infrastructure, as well as common primitives with the video framework that we had. So essentially what it gives us is we can have the devices in Comcast Network and still be able to use the common infrastructures like logging and telemetry and other device manageability, stuff like that. So we were able to leverage that straight into the broadband profile as well. And right now it's fairly new, introduced early this year, and we already have almost 2 million devices in the field, and probably it will be over 10 million over the end of this year. So some of the features essentially we have, the gateway is a single device. We have DOCSIS in there, and it also have the voice part as well attached, which we do not kind of like provide that as in source. It's generally a IP that is provided by the SOC vendors or the OEMs. What we do provide is we have a HAL layer which is designed to talk to these subsystems. I'll cover that in one of the diagrams later on to extract various information, but these are fairly independent systems. It has the captive portal for Wi-Fi as well as a public Wi-Fi for offering hotspot facilities that Comcast offers. If you use Comcast in US, you have this Xfinity Wi-Fi, for example. MoCA is essentially for all the cable connections that is in home. So we have the MoCA drivers and the MoCA APIs that are available. So anybody who is designing a device to operate into cable operations, you basically implement the MoCA APIs and provide the MoCA hardware. What you see is we also have the cloud gateway support and HNAP protocol support for home security. So those are generally the framework which is built on top to manage your device locally. And then it is also extended to the cloud. So we are able to talk to backend where you can offer all those services to a portal on the web to the customer. And the gateways are supporting both dual band Wi-Fi AC, and provisioning is another architecture which is a very strong point of this RDKB. When you have operator kind of scenario, service provider scenario, then you need a common provisioning architecture, which is again part of the RDKB features. And WPS, it's a generic feature, and SNMP and TR69, we carried over those from our RDK video for manageability, but then there is an enhanced protocol for managing. I'll talk about that, which we call WebPA. So some of the unique features that are specifically used by Comcast in general is the HTTP code download. The XConf is our head end, which manages the device code download and upgrade infrastructure. WebPA is essentially web protocol architecture. It's a WebSockets-based architecture, which is meant to talk to our cloud. And there is a client sitting on the gateways, or any device for that matter, which can have the client and then be connected to the cloud for manageability. The RDK logs is a logging mechanism which is specific to RDK. We use this specific format to collect logs from the devices, and all those logs are then hashed into backend servers, which is then using various technologies like Splunk. We extract a lot of information about our device health, downtimes, and failures. RDK Matrix is another feature that is device reports voluntarily, or you can request from the head end specific information, and you can also tune in to get information about various features on the device. So RDK Matrix is collected specifically if you want to monitor data usage or device parameters, then you can configure that from head end, and also the frequency of data collection. So it can be fine-tuned from various components. Then it also has the features like self-healing. If something goes wrong, it can recover itself. And also the RSSI, which is for your signal strength indication. So you can get a little information about what is your network's noise levels that are available, or that are currently in your network right now. So we are also actually extending all these further to give a very comprehensive view of your home network. I'll cover that in a bit. So these are probably some of the IoT features. By the way, today, what we have is a complete Wi-Fi gateway. We have spent a lot of time in getting all the Wi-Fi features in there, and we are extending right now to other IoT-related things, Zigbee, Thread, and Bluetooth LE. We do have implementations of those, but they are not yet available to the public release. But it's still under works right now. So the key there is that we have this device system bridge. We believe that all these technologies needs to coexist. So we are not going with one of them, say use BLE and don't use Zigbee kind of thing. So what we are developing is something called DSB, which is the bridge between all these three, so they can interoperate if need be on our gateway. So the DSB infrastructure is currently under works. We hope that right now we are at 2.1 release. In April, we'll have a 2.2 release, which should have the DSP infrastructure available as well. Similarly, all join OIC you might be familiar with. We are developing another connectors which will be able to connect between these infrastructures as well. And similarly, there's a cloud adapter again, which is part of the WebPA infrastructure, which is very generic, works on WebSockets, and we believe that it can interoperate between multiple cloud implementations at the back end. And we are also working on secure onboarding of devices, which would basically create a temporary SSID for onboarding purposes, seamlessly onboarding a device and then getting the SSID turned off for that particular onboarding procedure. So this is also something that is being worked on currently. The rules engine is essentially, which is constantly being developed. Right now it is in operations. Right now it handles the hotspot capability of the gateway right now, but more to come to the rules engine as well. So why should we use RDKB? So essentially, a lot of people ask questions, why didn't you go with OpenWRT or something which is already available? So there was an analysis that was done, and one of the common features that we needed to develop with OpenWRT anyway was our infrastructure for provisioning and talking to our backends, for example, for our head end. And we needed a common architecture that we can extend. So, and various implementations of OpenWRT that we came across have actually modified OpenWRT to their own needs, and sometimes have put in major components in there that were not available as part of OpenWRT and so on. So, essentially, we also needed supporting various TR protocols that was already in our network. Essentially, TR69, which is currently used by our video devices as well for managing. And then, so all those features were already available in RDK, and we wanted to extend them in. So essentially, that is why we extended RDK to a broadband profile rather than using a different infrastructure. And so talking about RDKB, I'll show in the architecture diagram. Basically, it is a heterogeneous architecture. It's also distributed in nature. It has a component registry, and every component registers with it. It has runtime APIs. So you can register your APIs at runtime, and the component registry will be able to tell you what version of component you are running, and every other component will be able to discern that and interact with that particular component at runtime. So there are no static APIs per se. So you can update a component and it will still fit into the system. And what it uses underneath, it uses D-bus architecture right now for IPCs. But it is also extendable. For example, one of our broadband gateway designs have dual CPUs. So we can actually run RDKB services across 2 CPUs or more CPUs and have a RPC mechanism to communicate all the control signals between the components as well as the component registrar. So, and this is not limited to 2 CPUs on a single device. You can also virtualize it if you want to, where you can have maybe VMs, for example, running services and talking over network. It can be extended to that level, but we don't use that mechanism right now. We based on the whole infrastructure on top of OpenEmbedded to get a lot of packages available which were vetted already by the infrastructure, and we could easily bring in all the open source components that were required to support the RDKB middleware and other features that we are currently developing and have requirements on open source components. So it's easy to bring in those component dependencies. And we right now are working with getting all join to work as well as IoT. And of course, the logging infrastructure I did talk about, for example, which is a unified infrastructure that you can deploy and can be used to collect a lot of information actually from all those millions of devices which are in the network to create better services and also do analysis on any failures or downtimes. So WebPA stands for actually Web Protocol Adapters. So it's actually a suite of adapters. What it can handle is it's taking the messages from your head end to the device and vice versa. And it understands the TR-181 model for message passing. In addition, there are more models which are added on top that it can do. The basic underlying technique it uses, again, the WebSockets. So and then uses a JSON format to encode all the messages across the network. And WebPA has two components to it. One of them is the server component, which is dealing with the communications from your cloud into your, and there's a client piece which is implemented on gateway or any other device that you would like to connect to to your cloud. WebPA is actually available as open source. We have made it available on both the client side as well as the server side. So they are already in process of open sourcing it. It's already approved to be open source. It will be available on GitHub. Probably half of the components are already there, and hopefully by end of this week, the rest of them will also show up. Right now, we provide the emulator implementation. So right now you can, we have created a emulator platform which can act as a access point at this point. So you can have a USB dongle and then run RDKB, and then it basically starts behaving as an access point. It can emulate a lot of features that RDKB has, barring any provisioning and you know, any of those DOCSIS or MoCA and all those things. But the top level gateway functionality, routing functionality, and then firewall, those are all emulated on the emulator. And this is what is currently available if you go to the CMF, which is the code.rdkcentral.com. We also have actually provided a layer for OpenWRT components. If there are any components that anybody needs to add to RDKB, there is a simple OpenEmbedded layer that is available, and you can choose the components or even replace the components in RDKB if you wish to. Because OpenWRT has their own IPC implementations, their own network daemon, and stuff like that. So that is possible, although we haven't tried that with RDKB. Through our APIs, we have achieved a good separation between our modem and voice and data, actually the three functionalities that our gateways do right now. As I mentioned before, we don't have the modem firmware and the voice firmware, for example, has APIs to access information from there. And the data piece is where the routing functionality and all those are actually part of RDKB. So this is actually what it looks like. What you will see there is that it has this get parameter values and set parameter values, add to the table and delete from table. So this is how you add or delete certain APIs at runtime for a particular component. And you can generally build the data, the runtime database for all the components and all the different APIs that they support. And when a message is sent from one component addressed to another component, the APIs are verified, and then the other component knows the versions that the previous or the sender is sending the information from, and it can take action based upon the version of the API or version of the component that is currently under play. This gives a very good runtime architecture. Actually, you don't have to change your base packages. You can add components or upgrade components and not change the rest of the system. Although we haven't yet used this feature where we would update our components on the fly, but this is a baseline set for future when you have IoT devices which you would onboard. That may not be part of the existing firmware that is on the box, and so we hope that we will be able to leverage this architecture for onboarding those kind of devices as well. Right now, as you can see, Wi-Fi, for example, is one functionality that is plugged in here as a sample. Similarly, it's the same method that's used for other kind of interfaces as well, where it has the provisioning architecture, which is common, and it understands the interfaces, and you can provision any kind of interface, any kind of device, and then register them to the central registry mechanism, which will then make it available to rest of the components. So this is the component diagram. If we look at the number of components that are available today, and what you see with various color codes is who kind of contributed to various pieces, or when this is being ported to a different device, then what are the pieces where you play the role to port RDKB into your particular systems or your SoC, for example. So as you can see, the blue portion is essentially the CCSP component. CCSP is a common software architecture that was contributed by Cisco into RDKB, which manages the device and all the peripherals and all the interfaces, and this is core of, if you say, the RDKB. And the features that you see in blue, like TR69, SNMP, PA, those are protocol adapters that I was also talking about, which are then used to connect to our cloud based upon various protocols that are used right now. The WebPA protocol is right now the predominant protocol that is used for connecting to the head end. But then there are other protocols that are also available if one has to use that. As you can see, there are then a layer below that you have a lot of features like DCS, dynamic channel selection, and then DFS, which is dynamic frequency selection. These are all targeted towards Wi-Fi right now, because we wanted to make Wi-Fi as sound as possible and make it possible to have Wi-Fi conflicts and let it kind of distribute the load over our dual channel, which is 2.4 and 5 gigahertz. So it has that capability to check how much clients are connected on 2.4 and can gracefully send a client which is trying to connect to 5 gigahertz channel. And all this functionality can actually be controlled from a portal on the web. So all this information is available through WebPA into your backend. And you can either provide a portal to your customer where he can see his network, or he can control various parameters and issue any control commands that he would like to do through WebPA into your device and into your network. Right now, a lot of work are happening around Wi-Fi, again, understanding the Wi-Fi characteristics in a house. It's a dynamic scenario. Every house has different different topology. So to provide a consistent networking experience in a Wi-Fi connected house is a very big challenge. Comcast providing video services, providing them reliably over Wi-Fi is a very big challenge. To maintain that quality over a period of time is a very big challenge right now. And so there is a lot of tooling that is right now being developed in there to understand and take actions on ensuring good Wi-Fi connectivity and throughput. And so as we speak, I think in next Connect, for example, I would be able to talk more about the Zigbee and Thread and rules engines and device onboarding, which is still work in progress. For Wi-Fi, we are also designing a API layer, which is part of, again, the RDKB infrastructure. When someone ports their Wi-Fi devices over to RDKB platforms, they will be implementing those Wi-Fi APIs for us to hook into all the DCS and DFS, all the functionalities that I've just mentioned. So we can get all that information for a consistent Wi-Fi experience in-house. This is all Linux-based, so we use a lot of open source components, as you can see in yellow, which are direct dependencies of the CCSP framework that it requires. And for managing the routing functionality that it has, it uses various bridges and soft GRE to do connectivity over creating VLANs and connectivity over your router for various other facilities that it can provide, like captive portal, where you want to control certain set of IPs with specific firewalls, and also have child control and other selective networks that you would like certain devices to be part of. In the dark blue, for example, is a normal user story bootloader platform software that is very common across all kind of devices. That is what is provided by OEMs, for example. And then SOCs, we expect them to implement all the HALs that we are designing for cable modem or Zigbee or MTA or any of the other pieces, Wi-Fi or whatever the new devices become. So there will be a specifications from Wi-Fi or other devices that will be available as sample either for emulator platform or otherwise that then has to be implemented, which is fairly simple. There are only probably 10, 15 APIs that you have to implement to hook into your particular Wi-Fi device. Similarly, for ZigBee, there will be probably a smaller set, and so on and so forth. So the core components, as you can see, RDKB says the message bus, which is implemented on top of DBus. And then it also has the OpenSSL-based security mechanism. And all the components are then hanging on to the CCSP message bus. And the message passing uses the normal DBus IPC mechanisms to communicate with each other. One of the new things that we are also doing is multicast IP over video. So we will be able to have some QoS mechanism to do video over the same gateway, which would understand the video traffic, for example. So there is work going on in that area as well. And self-healing, I did mention it a little bit. So all the tooling that is being provided into, for example, Wi-Fi system will provide a fair amount of inputs on self-healing. Spectrum analyzer is being developed, DCS, and then the band steering would basically give us a good balanced load average, and the frequency scaling would avoid any conflicts that we would have in-house. And of course, the process monitoring and then telemetry for providing vital data on the device to take action based upon what inputs it gets back can help for healing the device. So there is a self-healing infrastructure also being made available right now. So some of those are, we already talked about those protocol adapters which sit on the very top of the system, which talks over the network to your clouds. And then it has a provisioning architecture which is specific to DOCSIS and being also enhanced to do passive optical networks. So if you do fiber and stuff like that, then it is extendable to the fiber gateways as well. So this is just a list of open source components that it is relying upon, and all these components are right now provided to us through the OpenEmbedded framework, and we use them as it is. So you can basically get the base Linux distribution for RDKB, which is pretty much unmodified open source components, which are fed in from underneath and are being used by CCSP and other frameworks that we talked about. So these are I think probably almost all of them have no patches that are specific to RDKB. So we totally rely on whatever upstream OpenEmbedded gives us. So as you can see, these are like a separation of components that if you are a SOC vendor or you are designing a chip and want RDKB to be ported over to, then these are particularly the components that you would be working on to port onto your system. And most of them are the HAL implementations. And plus, you of course have the Linux kernel, and the base Linux OS is generic across all devices generally, but it's just added if there are any changes that are required. Generally, this is all provided by OpenEmbedded, so I think this shouldn't be in there. A lot of work for SOC vendors anymore. But profiling tools, for example, are sometimes very specific to a SoC, so you have to provide those backends for those various profiling tools to enable them on our devices. And GRE has a fast path. You can implement it. We rely heavily on that. And soft GRE is very compute intensive on CPUs, so we expect a offload, so a kind of a network processing unit there on the device. And then, of course, the implementation, the driver to offload the GRE traffic onto that one. And similarly, the other are very specific hardware components that will be part of your gateway that you will have to provide drivers or other software for. But it's a very hardware-only components that are to be plugged in underneath. So as you can see, there are no RDKB components that are being asked for here. So it's very well abstracted out that it is only interacting through drivers into the hardware. So there are no specific RDKB middleware changes that are required per device or per SOC, for example. So OEM components generally are around packaging and image creation, signing, and signing the platform software. Generally, they are overall taking care of packaging it, providing it in general, and of course, building it in the end, which is for release purposes. So these are the components that Comcast has provided and generally are available and are can be tuned to specific implementation if you take it to your infrastructure. They are very much adaptable. For example, hotspot setup, it may be that Xfinity Wi-Fi is the default, but that is not the only default. You can change it to whatever you provide as your service. Home security, same way. We do have all the necessary APIs to talk to various home security devices. It may have specific sample implementation that what we do that you can model on top of. A rules engine, same way. And IP tables generally to provide specific firewalls. It actually will be different for different kind of networks and devices. And then the local UI that we provide is based on PHP, and it has widgets and everything that are available, but they are easily, you can override them, you can add your own icons or any of other things that you can customize UI to look like yours. And the Wi-Fi resource manager is another component that is very generic, can be used as it is. However, all the data it collects from your device, maybe you don't care for all the amount of data that it gives you. So you might want to look at it or use it as it is and get the resource management capability. And tuning, the profiling, for example, for broadband profiling we talked about, that's also part of it. So speedtest.net and all. It also provides you the device manageability daemons for code download and system upgrade. So there is a sample implementation that is available. You might be able to use it as it is. Or if you have your own implementation, use your own protocols, you can replace it and change it if that is required. So zooming in into the components that are part of RDKB, in general are, so this is just the CCSP piece of it. What it shows is you have the CCSP message bus, and then all the components are then connecting and talking to each other over those bus architecture. And what you can see there is that most of them, for example, are already available, and the ones in blue, for example, are being added. And generally, what they have in common is the CCSP interaction. You can always throw in another component at any time, and as long as it has all the registration mechanism, it will be available to, or it will be known to other components, and it can interact with them, extract information about various stuff, and play in the RDKB infrastructure. Getting access, it is hosted by RDK management. So RDK management hosts RDK video as well, and RDK broadband is hosted at the same place. It is available as anonymous access. You can look through the source code through all the components that I talked about. And of course, OpenEmbedded being open, you can go and check out OpenEmbedded and build it on top. We test on OpenEmbedded 1.6 right now, but it should just work with 2.0 as well. We do have some next early versions which are working on 2.0, but we don't have anything deployed with 2.0. WebPA, which is our server and client infrastructure for IoT connectivity, is in progress, actually right now being open sourced into GitHub/Comcast, so you can keep checking there for WebPA, and they should be available. Some of them are already there, and all the development for WebPA in future will also move to GitHub. So it will, we will internally consume what is on GitHub, essentially. So all the development, all the features will come into GitHub before we use it. The RDK community access is available because the manifest and RDK OE layer that builds it has few components that would require you to be a member of RDK community. In order to build it fully the way we build it, you will have to go into RDK community and become a member, which is actually signing up there, and that's all. And download the manifest and the OE patches that we have done that are required for here, and the BSP layer for the emulator is also there. So it should be possible for you to build the emulator version of it. Everything that I talked about should be available and buildable. And the emulator we provide works on any you can use any of the emulators that are available for running them. And we do have, I think, extensive documentation on RDK community on process of getting the manifest down and building and everything. You should find all relevant documentation there. Right now, it is also being built, but not being tested right now as by RDK. RDK-M has a test bot where the video pieces are tested regularly, but RDKB is still not at that point. Hopefully, eventually, I think in a few weeks, it should be built and tested regularly by them. So that's pretty much I had. So any questions or comments? Yes.
Regarding component-based architecture, are you identifying compatibility or what other compatibility commitments to be making?
Yeah, I think so. The question is on component-based architecture, what is the backward compatibility story? So, what happens is it's a runtime contract between the components, and they understand various API versions. So when a version advertises itself to be 1.2, so the APIs are version 1.2, and if a component says, I don't understand 1.2, he will gracefully reject it, that I cannot understand 1.2, and then you can tool in a mechanism in a component to resend a 1.1 message if you are needing that kind of upgrade path. But generally, it will be able to act for multiple versions. So a particular component will come with, say, 3 versions, and various components can inquire, I understand 1.1 of your APIs, so here is my message, and he will be able to handle it. 1.2, he will be able to handle it. 1.3, he will be able to handle it at runtime, because the API versions are being sent by the components.
So then, in terms of your commitments for maintaining up to certain versions, are you saying that you will maintain just the latest 3?
Yeah, I think as of now, we don't see any kind of a flooding of, like, API, we having zillions of versions of API contracts to maintain. If it comes to that point, we might have to consider a version upgrade, but we believe is the major RDKB upgrades are kind of a point where you can expect it to say, I'm at 2.1, now I'm upgrading the whole system to 2.2, therefore that is my baseline kind of for my API compatibility, which would be probably, once, twice a year or something like that. So we don't expect it to explode so much. Yeah.
Have you done anything with Bluetooth or ZigBee?
Yeah. So question is, have you done anything with Bluetooth or ZigBee? We have started working on it right now. I can't tell much on what progress we have made yet right now. What we are looking at is, basic support at kernel level and making sure that, the existing devices we have don't support BLE right now. So, these are features for our next generation gateway, which will have all those, capabilities for ZigBee and Bluetooth LE. So yeah, we are doing work on that right now, but, we have nothing to show. Mm-hmm.
More like a whole drawing kind of application.
Mm-hmm.
For ZigBee, for example, if you use thread, so the gateway needs to do something with the messaging.
Correct. Yes, that's right. So for ZigBee and as well as for Thread, if and for that matter, we will have this adapter technology. So adapters are being developed, which will then be able to interact with the CCSP bus. Yes. Yes.
So, for example, if there's a different IoT network property, you may need to extend certain message types that is not currently foreseen, for example. In that case, how do you, the RDK family, how do you define this message?
Yeah. So I think that's a good question. What we are kind of hinging upon right now is our WebPA architecture, basically, which is a TR-181 object model, right? So what we are kind of hoping is that we will be able to take advantage of the same architecture and not have so many of different kind of messages that the bus has to understand, but it will be encapsulated, hopefully, by the time it reaches the bus. So the whole manageability of the device will move off onto the cloud, and the WebPA client basically will understand those protocols and then decouple them into these various devices on which are available on the device.